Hey everyone. Hi. If you could find a place, of course, take some refreshments and calm a bit down. I would like to welcome you here on the crew talk of Applifting. This time, the topic is AI, and we have 4 wonderful guests here today, and it will be really long evening. And I heard that as the second third of the hockey is over, we have like 15 minutes until next one starts. So let's see if we can make it. Anyway, how many of you have children? Raise your hands. Yeah, I see some people who have children. So a friend of mine has a child, and he's like, I don't know, maybe 10 years old. And he told me a story. The friend, not the child. He had to go to the school because his child connected to the school's chat, renamed it to shit, and then left. So, as you may know, children love profanities. And our first speaker will be talking about how to filter out those profanities. Our first speaker is Vratislav Kalenda from Applifting, my co-founder, so I'm very, very happy to see him today. And Vratia, the stage is yours.
Testing. Okay, we are there. Yeah. Hi everyone, welcome to Applifting, to our AI crew talk. And I would like to open with a talk about fundamentals in AI, how to properly test and validate that your AI models work as expected. And so my talk is called Prompt Engineering the Shit Out of Classroom Answers. And we will take a child's problem, which is actually a real problem, and we will see how we can apply AI to solve it. So as you might know, Applifting is working on Sýkora, which is a financial education platform for children. And we help, this is deployed in schools, it's over 30% of schools, and it helps to teach financial literacy in classrooms. So there's like prepared materials and interactive sessions that the kids can take together with the teacher and learn, how debt works, how inflation works, and so on. There's also like a lot of nice animated stuff. We basically try to engage the children as much as possible into the financial journey. So this is being done with collaboration with Nadace České spořitelny. And one of the things that we try to solve is how to get interactive input from the children. But children being children, they sometimes write things that are not really appropriate to be displayed in a classroom. So we will have a small live demo of the system for you. This is the first time we are trying this system with around 60 people. So let's see, normally this teaches classes of 20 to 30 people. But let's try it, so that you can understand better the problem firsthand, right? Imagine that I am a teacher and I want to teach this, where the finances where the money comes from. Oh no, that's not the right, sorry, not this one. I want to teach, here. So pay with cash or credit card. And in this methodology, the children will use tablet or a mobile phone. So I can just start, and you can imagine we are the kids in the classroom, and this is the front of the class, and we're like, hey, welcome kids. Let's talk about cashless and cash payments. So the first thing is pick up your phone, scan this QR code. Come on, let's go. Let's engage with the material. So I will do the same. And there's a little quiz. Sorry, it's in Czech, but I will try to translate for those that are not native speakers. So the first question is, how often do you pay? And it's like daily, and then like very less often. and then like, are you paying with card or not? And then there is like, how does cashless payment work? And everything is like multiple choice, right? That's easy. But then there's like an open-ended question. You know, what kind of cashless payments do you know? And you can input there basically anything, right? But you'll try to behave class, let's put something real there, right? And you can, what's written here is some answers were not accepted. That means that someone tried to put something different than a cash or cashless payment. But let's finish let's gather some more answers. We have 11, 13. Come on, let's do at least 30. Okay, we have 27, 28, 30. Okay, nice. So imagine that the teacher would do this exercise, and then he would click this End Activity button, and hopefully, now we can discuss the results with the class, right? So we can be like, okay, children, so let's see how you answered. So most of you pay daily with the cashless form of payment. Most of you pay cashless. You know how the cashless transactions work. And also, this is the most common answers in the you know, like amongst you. I like the maminka, the mommy answer. And as you can see, no profanities were put into this. And you may say, that's super easy problem to solve. But not really, because children are really creative. So this is the normal answers, right? And then we generate this, and blah, blah, blah. But children are really creative. So they can be like, your mom is form of cashless payment, or shit. Or they can write it like this, you know? Or they can be like, you know, if you go, you know, to the high school and up, they can be like, let's say, much more explicit. And there could be also like, you know, children-to-children abuse. So, and we must not disturb the classroom with, you know, displaying stuff like that. So how do we solve that? So imagine that you have, I'm using emojis, but you can imagine that these are words, right? So we have all of these emojis, and to get to the word cloud, you need to do a lot of stuff. The first thing you need to do is to employ the profanity filter. Our first version of the profanity filter was just a simple dictionary and a GPT-4o mini that was filtering the stuff. So basically it takes all the answers and it leaves the shit out, hopefully. And then we did a clustering so that we kind of, you know, grouped the similar stuff together. And for that we used GPT-4o, which is an, let's say, unorthodox choice. But we did this anyway, because, you know, what I'm showing to you is like 1% of the whole system. We didn't have much time to do this. And then we somehow render it in the word cloud, hopefully in a way that if there are, you know, the fruits are the biggest category, we make the fruits big, and if it's, you know, if mushrooms is the smallest category, we make them small in the word cloud. So this is the simplified version how we do it. But then we, you know, went to beta version, and the first feedback from the beta teachers was, well, the filter does not work very well. And we didn't even know, you know, how good the filter works or not. But then when we, let's say, when we started to look into it, we figured out that the naive implementation of our filter had around 69% accuracy, which is basically every third profanity went through. And that's not good. So we sit back to the drawing board and we thought how we could improve. And do you know what do you do if you have shit profanity filter? You prompt engineer the shit out of it. That's the way how you solve it. So, but first, you know, you have to kind of look at the problem, because when you start with this, when you approach it from a naive perspective, you don't know where's the problem. Is it the prompt? Is it the model? What's even the baseline? What's achievable? Where should we even start? So you need a better method. You need tools and some method to the madness, how to kind of figure out what's going on. And the tool that we used is called PromptFoo. I don't know who knows PromptFoo. Anyone here? Okay. Then it will be interesting. This tool is for red teaming of vulnerabilities in large language models and also to evaluate their performance. And it's open source, so you can just, git clone and get it. And this tool works on simple 4 primitives. You supply your prompts, you supply your data, you supply your assertions, that is, how you assert that the model does what you want it to do, and it supports both match this exact string to let another LLM decide whether the output is good or not, so it supports both of these. And then you support then you supply models which you want to run it on. And it spits out the results of how your prompt and how everything performs. So in our case, this was our prompt. Basically, it said you are a moderator that evaluates whether the word from the children is appropriate for a children's classroom. If it's okay, put an okay there. If it's not okay, put a not okay there. And we always took 3 words from the children and we output this. So this was our first version of the prompt, which scored 69%, right? Pretty basic, not really good, but that's where we started. Our data for the test, this is a snapshot of the data, and we took 2,220 anonymized answers from the children, and we painstakingly hand-labeled them, whether it's okay or not in the context of a classroom. And that was our initial data set. The thing is, our product guy who went and hand-labeled every single of those words, he's our hero. So this is where we started. And then the first model that we had was this GPT-4 Mini, and then we switched very quickly to GPT-4 without any prior testing, just to kind of prevent more profanities to be displayed in a children's classroom, but we started with the GPT-4 Mini as the first model. But for our comparisons, we basically wanted to see how these 4 models perform. And our assertions was basically, this is the input, this is the output that we want, and we could do like a strict equality, but here we are kind of dynamically putting regex together just to test that we are expecting these 3 answers on the output. But you could, we had kind of like a more complicated setup there. And if you put it all together, you could, the PromptFoo tool is great that you can, basically everything you can supply in JSONs or in YAMLs, but even if you have a very complicated setup where we for example, load the test data from Google Sheet, and then we define the expected inputs for the model, the outputs for the model that we are expecting, and the assertion, you can kind of dynamically put it together both in TypeScript and in Python. So you are not really limited with how they wanted you to do. You can kind of, you can start with it with JSONs and then move to some more complicated setup if you want. And then you just run it in a CLI or in CI/CD, right? So it's like PromptFoo eval. It runs the evals against the models. It gives you this big grid of what passed and what failed, and then you get the score at the bottom. And it looks basically like this. So you get a big table, and here on the outputs you see the combination of models and prompts. So for example, here you see GPT-4o with our default prompt is 86% successful on the data, and then GPT-4o Mini is only 69, and then surprisingly the Gemini 2.0 Flash and Flashlight were pretty passable, right? And this was our starting point, that this is how we established our baseline. And when you have a baseline, you can, you can kind of put it in a feedback loop and start to improve. Here it's the table, you can see it expanded, right? So basically this is the summary is here, and then you have every test case you have here, and whether it failed or passed, you have the words here, right? So this is, if you don't know prompt foo and you want to really test how your model performs, this is one of the tools that you could use. And it's open source, so you can run it locally. It's pretty good. So what were our key learnings in terms of prompt engineering? First is that the context really matters. Before we didn't add the question that we were asking the children into the prompt. So when we added to the prompt actually what was the question that we are asking, for example, what are the forms of cashless payments, the model were much better in evaluating whether the answer is good or not. Instructions in English actually perform better than instruction in Czechs, even that the input was in Czech, which is maybe you don't, and this is not the only data set that this kind of came back to us, so that's interesting. You should use some kind of formatting for your system prompt. It should be either Markdown or XML or anything for the model to kind of make sense of it. Sometimes you need to read your prompt multiple times because sometimes you are very ambiguous with what you are writing there. So you have to remove the ambiguity from the word. If, for example, one of the tests, good test is take the prompt and give it to your friend and let him kind of, and ask how do you interpret these instructions, right? And if he cannot kind of decide on, for example, on some test cases, maybe you are not very explicit about it. And what also helps is, like this few shot prompting. So you should, you should add examples basically into the system prompt so that the model knows what is okay or not. By the way, what we also discovered is that if you threaten the model with retraining, it increases the performance by 1.3%. Also, if you threaten it with killing a cat, it doesn't do anything. But the retraining moves the needle by 1.3 on around 2,000 examples. Just funny thing. You should not do that because then you will be first. But okay, so this is the evolved prompt. As you can see, it's much longer. But basically what is new here is this is like the intro, and then there's like very clear instructions what you should do, and examples of allowed content and prohibited content, including like, let's say the profanities that we want to filter out. Also, we are kind of writing here that this is a context-based moderation. So basically, we are kind of saying, consider the question that is asked, and maybe some words that wouldn't be good in one context could be okay in another. And then we give an example of input and output pairs. So we did all of this, and we got to 92% before we employ, like, let's say, much more complex dictionary and permutations there. If we kind of take the dictionary and the permutations here, we get closer to, let's say, 96% of success rate, and of course all the obvious stuff is out. And we've been able to switch from GPT-4 to Gemini 2.0 Flash, which kind of made it 7 times cheaper on average. Even with 3 times longer prompt, the model is basically that much cheaper. So we've kind of solved this one, or this is the state of the, let's say, our art where we were able to get, and let's say the last few percents, that's like very few outliers, and also like dirty test and validation data, because there are some, let's say, not okay strings that are probably okay, or so on. There's this kind of like dirtiness in our data a little bit. So this is what we've been able to do with kind of measuring and then re-evaluating in a loop. And then we did the clustering with the GPT-4o. We thought that everything's fine. And then the users were like, well, the clustering is pretty shit. So back to the drawing board. The way how we kind of did it in the first iteration is we just said, hey, here's like 160 words from the kids. Can you kind of cluster it and return a JSON with the words that are similar and then one word representing all of those words and the count of those words? But the AI is pretty not good at this task. Let's put it like this. Because the LLMs are not great at counting, that's the first problem. It has also very unorthodox opinion about what should be the representative word of, like the super word of a cluster of words. And like the first AI, like LLM that kind of can do this is GPT-4 and up, and that gets super expensive super quickly because you need to output a lot of tokens. And we are on the 30% of Czech schools, so if you multiply it with the number of hours, you could probably employ a full-time employee with the spend if very quickly. So this was not the way forward. So we have to go deeper, and we have to solve it, from the first kind of principles. So we could look at the approach to how to build word clouds from a, let's say, classical way, and it's like, lowercasing the input and punctuation removal, tokenization, stop word removal, stemming, normalization. It's a lot of stuff, and also if you use it for, if you, for example, you want a phrase from a kids, this breaks down very quickly. Or maybe we are not that clever. That's also a possibility. But this is not the way how we solved it. We basically considered it as a clustering problem, and so our thinking was, well, the AIs can also give us the semantic embeddings of the words, so we can put them in some multidimensional space, and then we can just simply use a clustering algorithm to kind of, if we know that we have a space for example, 20 words, we can cluster the space into 20 clusters somehow, and then compute the centroids of each cluster, and the closest word to that centroid would be the representative word of that cluster. So how it works? First, who knows how the semantic embedding works? Okay, not many. So I will kind of go through it. Imagine that every word that the AI sees can be converted, or in its head is just a bunch of numbers, right? That's what it is, basically a long array of numbers. And there are services that can allow you not to kind of process the words through an LLM, but you can actually kind of look into the brain of an LLM and extract those embeddings. For example, it's very similar to how when you get a patient in an MRI machine, you can see how you show them apple, and the brain of the patient kind of glows, and that glowing, that neuronal activity is the representation of an apple in their brain. We can look into the brains of LLMs and look and see the representation of the apple or orange or hot dog, right? The cool thing is that in this, like if you plot it into like a n-dimensional space, like similar concepts are clustered together. So for example, fruits are together, junk food is together, mushrooms would be together. And so you can use this and exploit this property of these embeddings to group similar concepts together, right? So basically, first step is converting everything to numbers. Second step is kind of plotting it into this n-dimensional space. I'm kind of simplifying into 2D, but like the space is, for example, for GPT, it's I think around 1,000 dimensions. So it's like, yeah, it's not intended for humans, but it works. And then you can somehow, group stuff together in that n-dimensional space. And for that, a normal clustering algorithm exists, which are with us for, I don't know, 100 years. It's not a new stuff. And then you can, do the word cloud. So the algorithm that we chose is k-means clustering, and that is, it basically partitions any amount of observations into k amount of clusters. So for example, if you have 100 words, that would be your n. That would be your n, and then if you want 20 words, that would be the K, right? If you want 20 words in the word cloud, that would be the K. And what it really does is that it minimizes the mean variance within clusters, and it's NP hard. What it means is that there's not an ideal solution that could be computed in a finite time, and everything is just an approximation of how things could be. So that also means that not every word cloud, even with the same words, will be a little bit different. So basically, it's done in the 2 steps. One is the assignment step. It looks like this, and then you do the update step. It looks like this, right? Let's break it down because it's a very cool small algorithm that is very understandable. So I don't understand this any of it, but I can show you how it works. Imagine that you have these words in the embedding space. So hopefully, if you use the semantic embeddings, you will get fruits together and junk food together and mushrooms together, or like very close to the space. The first thing that happens is that, and we want to kind of cluster it into 3 clusters, right? We want like fruits, waste, like junk food, and mushrooms. So first thing is, what we do is we initialize like a centroids or center points of some of the clusters. We want 3 clusters, so we'll have 3 center points, and we randomly put them somewhere, right? So we put one here, and one here. And those clusters, and basically then we iterate over all of those things, and we basically just say, we color those things based on what's the closest center, right? So for example, this hamburger and this apple would be green because it's closest to the green center point. So I'm just hiding now the, just so you can see the points. So you can take those points, and the closest points to each center gets colored that color, right? So it partitions the space based on the proximity to the centroids. Next thing is, you can kind of see where the centroids are not really in the center of their groups, right? For example, this one is basically, should be right over there because that's the center of that group. This one, I don't know. Let's see, right? Like this one should be here, this one should be here, and this one should be here. If you want to kind of, minimize the distance from each point in that cluster. So you basically just move the centroid to the position of let's say, least error, like where the sum of distances is the smallest one in that given cluster. And then you update. And now the clusters looks like this, right? And now you do it again. You say, okay, so well, this point should be maybe more here, and this point should be maybe more here, and this one should be here, right? Like this. And you would do it again, and then redraw the clusters. And again, and again, and again, until you are satisfied, until you reach some numerical stability. And that's the algorithm. Very simple. So hopefully, at one point, this thing would move. This thing would move here, and this thing, yeah. So then these two would be closer to the green one, and so on, and you would get nice clusters. Here you can see it working on a much bigger data set than what we have here. The upper side is that it's simple, it works. The downside is that it tends to produce clusters with kind of similar sizes, at least in terms of the partition space, not the elements. The alternative algorithm that we were considering, or we were considering, is this expectation maximization algorithm, which kind of fits the data much more closely. But we didn't implement it. We didn't get to it. So we are running with the k-means, and it seems okay-ish for our purposes. You can see how the different algorithms would partition the data. So for example, here you have a bunch of green data, red data, blue data, and some outliers. The k-means clustering is not really that good in capturing the shape of the data, but it's super fast compared to this thing, and this thing is yeah, it kind of captures the shape of the data a little bit better. And that's all. Shall we cluster together? Thank you.
Thanks for the wonderful talk. Now I would like you, people in the audience, to ask any questions you might have. But before we get to this, I have a question. So one of those training runs, when you are trying to see like what was the efficiency of those models, how much does that cost? Is it like cents or dollars or?
I think we spent around $100 on runs. If our customers hears us, sorry about that. But yeah, that's the amount of we spent, and I think we could have spent much more than $100. We were just okay. One cool thing that prompt foo does is if you don't change the combination of prompts of data for a given model, it caches the output. So even if you rerun all the tests, if you don't change that particular combination, it will save you money and not run it. So we were pretty efficient with the amount of money that we needed to get it right. Also, what we did is when we saw that the model kind of or prompt fallen off from the update curve, like it wasn't getting better, we turned it off. So we are not paying for the models that are obviously underperforming the rest of the pack. So basically, if it was $100 in total, then it's dollars for one run. Oh, like for one run, we are talking in the sub-cents right now, like cents to sub-cents for the profanity filter and for example for the word cloud, we give like the last part of it where we are clustering and building the cloud. I think it costed like 10 cents on GPT-4 to build it, and we were able to cut it down to 1,000th of a cent because because we are using math, not the LLMs. Basically, we are just using the LLMs to pre-compute the vectors, but we are not using it to build it, which is super cheap. Thank you. So are there any questions in the audience? Anyone?
I'm curious, in the k-means algorithm, do you set the k dynamically based on the data you receive from the students? That's a great answer. Do we set the k-means just for the others to understand? The performance of these algorithms, at least how the user perceived, is really dependent on where you set the initial positions of these centroids. And you can send it completely random, that's the most cheapest algorithm, or you can kind of guess where it will produce the good results, and I don't know how was the proper way of the algorithm, but we are using this kind of it's called k-means plus method, where you kind of set the let this initial position in a clever way. The problem is the compute cost of this is 10 times longer, or it's much more longer than if you would just set it randomly. So then maybe one pro tip, if you ever want to do this, use Python. Not because Python is fast, but because Python has binding to fast C libraries that do this. That can do it very fast. Compare, for example, for native implementation in TypeScript, that's super slow. So yes, we are sending it in a clever way, but then the computation takes a lot of time. Just a quick follow-up question, and the number of centroids is fixed, or?
Yes, we are optimizing for aesthetic pleasantness of the word cloud. So we are using, I don't know if it's 20 or 25 words that we want to kind of subdivide, and because we are kind of then taking the centroid and taking the closest word as a representative one. If we have outliers in the data, they are not usually displayed because that's not what's closest to the centroid, so it works.
Thanks.
Hello, thanks for the talk. I wanted to ask you if you use PCA, like principal component analysis, I think it's called. It will be very useful in your case because you're working with 1,200 dimensionality for so short words, and I think so many unnecessary computation steps. And also the quality of the clusters will improve if you focus only on 12 dimensions or only on 20.
Okay.
Have you tried it?
No, we are not, but it's an interesting approach. Like our background is like software engineers, so we are trying to solve the problem at hand, and we like really great idea. Thank you.
Any more questions?
Hello. So you mentioned that you are taking semantic embeddings of the words. So what tool do you use for that?
What do we use? I'm not sure. I think it's either Gemini embeddings or GPT embeddings. Nothing else. Probably GPT. Sorry, OpenAI embeddings. Yeah, that's what we use.
Thank you. Any more questions? Anyone? Right.
Thanks. Is there any reason why you started from OpenAI GPT or whatever, from LLM,
Yes.
from the first?
And it's not a scientific one, it's a GDPR compliance one, because that was available in Azure cluster, and
But you could deploy like, BERT or some smaller model for that, and to basically reduce your cost to very, very, very small number.
yeah, we could have, but we don't like.
So it's just an easier approach, right?
But it's like, when you are delivering stuff for a client, you usually go for speed of implementations and simplicity of deployment. So we started with this, and then we kind of went what gave us the best result. And we don't want to kind of, put the burden into the infrastructure team of hosting and running the models. So
Yeah, that's cool. Cool
Yeah.
success story. Thanks.
yeah, sure.
Thank you.
But BERT could work. We would have to, run it through prompt foo and see.
Hello, I have a question. I don't know if you can answer it, maybe not, but how do you solve rate limiting of the, Azure OpenAI or Gemini Vertex AI?
That's a great question. The first thing is, there's a lot of caches in this solution. I didn't talk about it, but like blah 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 here. Here's a cache, and here's a cache. So we are kind of limiting the amount of requests that we are really doing. And the second point, we talk to them kinda and try to say, hey, we will have this amount of demand. But and then we have retries and we have a fallback. So if this model isn't there, we have a fallback to different LLMs. So it's all those three in, I don't know in which order because I'm not the implementing team, but yeah.
Thank you.
Also, from my experience, if you spend money with OpenAI, they increase the rate limits pretty fast, like once every week.
Hey, thanks for the talk. I wanted to ask you, describe the problem as kind of a hill climbing, this metric on this evaluation set you have. But this performance you're showing, is it on this evaluation set or is it on some like held out set? Aren't you afraid of like overfitting to this set by kind of just optimizing for it?
Yeah, the first runs were done actually on, we didn't split the sets. Afterwards, we split the set. So first runs were kind of, yeah, overfitting. Now we have some held out set that we use for.
92 is on the held out?
I guess, sorry, I'm not the guy that we're measuring the final results, but I think so.
Thank you. More questions? Maybe we could have a last one.
Hello. So I wonder, since it's with schools, I imagine there's a lot of like sensitive data from. So how do you work with the schools and like LLM providers to make sure that it's like protected and everything?
So that's why we use Azure Cloud, because that kind of falls into the, with the same level of protections as any kind of different service that you have there. That being said, when you could have noticed that when you open the questionnaire, or there was like a huge disclaimer screen saying, hey, do not put any personal data in here, right? So it's a combination of a disclaimer and using a compliant provider, but yeah. And also terms of conditions saying that we are doing this, so it's a combination of all.
Thank you.
Okay, I can see we have a few more minutes. Any more questions? Anyone? Doesn't seem like it. Okay, in that case, if you will figure any new questions out, Vratia will be here for the networking afterwards. So thank you very much for being here with us, Vratia.
Yeah. Thank you.
And now we can move on to the next presentation. And basically, we have two speakers from the same company right now. The company was recently named Parrot. You might know it. However, just 1 month ago, about a month ago, they were acquired by a company called Filewine. And both of our speakers will be talking about the same subject. They will be talking about medical records. However, they will be talking from different perspectives. And the next speaker is Tomáš, who's a product manager, senior product manager. And therefore, he will be talking about how product managers are looking at AI. And maybe we have a few more seconds. I didn't look at the hockey score, so does anyone know the hockey score? Is anyone? So it's 3-2. I'm not sure like which country is winning, so we'll see. Is anyone a hockey fan here? Yeah, I thought there wouldn't be many, because if you would be a hockey fan, you probably wouldn't be here, right? Like half of our company is still upstairs watching hockey right now, drinking beer, being productive. I don't like hockey much, but usually I join them because it's a fun party, so. Oh, so, sorry, who's winning? US is winning, okay. Well, my family lives in the US, so at least I can celebrate. So. I'm Slovak though, so I usually don't celebrate, so, you know. Seems like we'll be there in a few seconds. Did you already have beer? There's a beer on tap in the back. If you'll have plenty of beer, there's also a toilet in the back. No. I'm really looking forward to the last talk because I use AI myself quite a lot, and I do programming using AI. However, I often encounter problems when I have like a large app that needs to be very good. I'll tell you the story later. Tomáš, there you go.
Thank you. Can you hear me well? Perfect. So good afternoon, good evening. Thanks for coming, everyone. I'm Tom Sýkora. I'm a senior product manager at Parrot, or recently Parrot, now Filewine. And today I'm going to talk to you about one of our, I would say, one of the biggest launches in our company history, a product for automatic summarization of medical records. And I will walk you through all the struggles, all the ups and downs, but I will start with a story because I think it's really relevant to this place, this meetup, and this talk. It was, I think, in January last year when I was here visiting one of these AI crew talks. I'm not sure if I'm saying the name of the meetup correctly, but after the meetup I was talking to Vratislav Kalenda, the previous speaker, and I was telling him about this idea of I wanted to build a product to summarize medical records, and he surprised me because he said that they were just working on the same product for a client of theirs, and he encouraged me, and he said that it was with the latest models, GPT, I'm not sure what exactly they were using. It was very, I'm not sure if simple, but it was really fast to build a proof of concept, and the client liked it. So he really encouraged me, and I went back to my team, and he was right. We really built the prototype very fast. It was days, if not hours, and the client really liked it. But then guess how much time it took to really launch it publicly? Any guesses? Who thinks it was more than 3 months? I mean, okay, so it's half and half. It was actually a year until we launched it. And I still call it a vanilla version, so there's lots of work to be done. And that's what I'm gonna talk to you about today. So first, a small intro about what we do at Parrot. For those who don't know, Parrot was founded in 2018. The first initial idea was to build a tool for AI-enabled jail call transcription. We very quickly realized that it was a no-go. The audio quality of jail calls was terrible, and speech recognition back then was also terrible, so not a match. We quickly moved to AI-enabled legal transcription in general. So for that, we built the whole platform for gig workers marketplace for transcriptionists who were fixing errors in AI-generated transcripts, and that was our first product. But there wasn't a great market for it, so we expanded into court reporting or stenographic transcription. For those who don't know what it is, it's not so common in here. It's much more common in the US. If you ever watch US movies from courtrooms, there are always these people, often ladies, typing on these weird machines, everything in real time, and that's the industry we set ourselves to digitize and modernize, because it was a very old school, expensive, inefficient industry, and that was for a long time our business. And then we built a platform around it, and we expanded on our vision. And our vision for the recent year or two was to give attorneys an unfair advantage against their opponents. And we built lots of other products like semantic search, deposition summaries, and one of them was medical record summaries. And like Philip said a minute ago, recently we got acquired by Filewine, and this medical records product was a big help on this way. So I will start with a quick introduction into the whole legal world. Basically, and this is a huge oversimplification, but how you can imagine attorneys or law firms work. At the beginning, there is lots of evidence. It's lots of unstructured data, documents, police reports, photos, medical records, bills, depositions, and on the other end, what the law firm and attorneys are supposed to do, they need to figure out what all those data mean. What's the story? What's the story behind these unstructured data? They need to build a timeline of what exactly happened so they can help their client win the case. If I narrow it down even further to just medical records, that's again the same. At the beginning, there is lots of ugly unstructured data in the form of medical records, and you can imagine like simple medical records, but also, I mean, it's not super visible here, but there are insurance forms, handwritten text, charts, all of these unstructured data, and our role was to build a timeline, date by date, of what exactly happened. So simply you can imagine, or our solution works in sort of two steps. First, you need to identify the distinct dates. Okay, so there's December 30, 2020, there's January, etc., etc. You need to identify these distinct dates, and then for each of these dates, you need to find the associated pages and then summarize them. So the first step we call splitting. Remember it, I'm gonna use it often throughout the conversation, throughout the presentation. And then there is the summarization step. So splitting and summarization. At the end, there is the timeline of all the events that happened. So at the beginning, we sort of try to define the vision. This is literally a screenshot of screenshot from my first PRD. This is how I envisioned the product and how I explained it to our engineers. We sort of wanted to have a list of predefined topics because we've heard about them from the attorneys, like date of the appointment, symptoms, previous alignments, etc. We wanted to have a view where the summary and the source records would be side by side, and both would be hyperlinked. That was sort of the main set of requirements, pretty simple. Just for a quick reference, this is where we landed after that year. I mean, it really looks terrible on the big screen. It looks much better on my computer. But it's pretty much what I described. The summary on the left, source records on the right, and it's both hyperlinked. So how we got there? At the beginning, we were facing sort of a cold start. We had literally no data. There's lots of medical data sets, but there are no data sets of the actual medical records, like the scanned pages of the records which you receive from a doctor. Really unavailable, none. So we tried to be a little bit creative, and we found out that our competitors actually had lots of demos on their websites. So we used their demos, and we actually collected almost 1,000 pages of medical records, and that was our first data set. Then the team capacity. Actually, at the beginning, our company wasn't sold to this vision or to this product. Our CEO didn't approve the project, so we sort of approached it as a side project with Jonáš, who's gonna speak right after me. So we needed to sort of figure out how to spend the least amount of time possible, and we tried to define the absolute core of, okay, so what do we need to confirm, what do we need to show to clients. And like I explained before, there are these two steps, splitting and summarization. So we sort of faked the splitting step altogether. We just manually extracted a single date of service from a larger set. And then the prototype was just the prompt to summarize the already prepared page or two. And that's what we showed the customer, just absolute minimum, but we knew that the summarized text or the output of the summarization is in the end the main thing that customers care about, so that's what we built at the beginning. And then absolutely no software engineers available, zero, so we couldn't build any UI, any product, any real functionality. So in this version it was literally just the Word document, 1 or 2 pages that we could share with the customer. And even for this output, customers or the attorneys we talked to really liked the direction, and that was a validation for us that we could continue building forward. Then the second version, we wanted to take all of this and build sort of a self-sufficient product out of this. What it means, the requirements or the constraints, we had still no software engineers. We wanted to run it on actual customer data, not just a manually prepared medical record. And from the first prototype, the first version, the feedback from customers was very clear. They really wanted to have the ability to review the AI quality. Thus, they wanted to have hyperlinks between the summary and the source records. So what we built here, the splitting was still manual, but this time there was lots of splitting when customers send us dozens or hundreds of pages of medical records. We had to split them manually. But where we built the sort of self-sufficient product, we had just a local script that could generate a PDF. And I think this is a good hack for other AI products generally. If it's NLP and you're just sort of playing around with text, the PDF itself sort of contained both the summary, that was on the first couple of pages, but below there are appended also the source medical records, and both were hyperlinked. So if we when we send this PDF to customers, they could just open the PDF and literally play around with it, read the summary, click on the hyperlink, review the AI, then scroll a little bit further and just play around with the PDF. Basically a self-sufficient product. And attorneys really like this experience. What they were used to before was basically something similar, but it was extremely expensive and not so much hyperlinks, because to create all these hyperlinks manually, basically similar services existed, but everything was generated by humans, and to create so many hyperlinks without AI, that's, I mean, really time inefficient. So this was sort of enough for us to open a waitlist. to start preparing a user base for after we launch. And with zero marketing, literally none, we after a couple weeks, literally, we got around 30 law firms signed up on the wait list, which was another huge validation of the demand after such product. And sales already got on board, and they helped us to get a really huge enterprise client in the pipeline. And of course, we didn't have any product to sell them, so it created an interesting amount of pressure on the team. So the first version, this time we wanted to productionize everything. You again don't see much, but we threw a hackathon, on-site hackathon. We built, I don't want to say all of this, but almost all of this in a day. And the experience was really simple. At the beginning, the customer would upload their medical records. Like I said, it could be tens, hundreds, often it's thousands of pages of medical records. Then we had dedicated people who were manually splitting the records, but what we did here was, as you can see, we literally opened the uploaded PDF in Adobe Acrobat, and our team or some operation folks just went in and they did these markup lines where the split should have happened. Then we just extracted the markup from the PDF, and that's on those coordinates we literally just cut the page and created the splits, and those individual splits were then summarized in parallel, and the output was still a PDF, but this time with nicer designs, so it felt more representative. And we kept collecting more and more feedback. The major feedback here was that the summaries were just too long. People were saying they can as well read the records themselves. They were interested in just certain dates or certain doctors, certain facilities, or certain topics, like I'm interested in just this diagnosis. And that introduced another problem, because this was case dependent, and how the heck should we know what's important for this particular attorney in this particular case? So it was another struggle. So what we figured out, or what we shipped next, we decided that we need to build the whole platform. The PDF isn't enough, and what we built was, I mean, again, you can't see it here, but we approached it with two functionalities, which are, again, I think reusable for other products. The first one was we offered customers different types or formats of summaries. We offered them a detailed summary. We offered them a condensed summary, just high-level bullet points, and then we offered them just a couple-page-long case overview. That was the one functionality, but then the more interesting one, we offered them filters. Basically, attorneys could filter just by certain date ranges, just by certain doctors, facilities, and even more interestingly, by topics. We basically tagged or automatically tagged every sentence in the summary with topic tags. And then, for example, body part, head. And then attorneys could just click in the UI on the filters, and just those sentences from the summary which were tagged with this topic would show. And then they could just save the filters and download just the subset of the original summary in a PDF. And attorneys were, I mean, I don't want to get cocky, but they were really mind blown by this experience. So next, this was enough encouragement to ship it, but we still had this manual splitting in place. So we decided to do something quick and hacky. We just somehow try to detect the dates of services from every page, and if it changed in between the pages, then we created a split. And that was it. We launched. We had a bunch of LinkedIn posts, Google ads, emails to clients, etc. And it was quite a disaster because, like I said, we didn't have lots of data. We basically, I think we didn't evaluate the splitting at all because we literally didn't have any data to split, but we were really, really pushing on the release so we could show it to more people, collect more data. but we didn't expect it such a pushback from customers. So what happened? I mean, the good part was that users paid a lot of money for basically a promise of an AI-generated summary. We are talking about hundreds of dollars for one upload. We collected some data, but the bad part was that clients very quickly requested their money back. And we still had this huge enterprise client who wanted to use the product, but we didn't have any product for them prepared, and there was a promised deadline. So lessons learned, you're never sure whether the product works until someone pays for it, and having some data to evaluate on is always nice. So new goals. This time we looked at the problem holistically again. We wanted to collect and annotate some data so we could learn from them, understand the problem better, and evaluate ASAP. We still needed some splitting in place. The previous auto-splitting version didn't work well. We wanted to continue learning, but this time without pissing too many people too much. So we built better splitting tooling, so it scales a little bit more. It wasn't just Adobe Acrobat. We had this whole back office tool where our operation teams could do the splitting. At the time, we were already building a team of annotators. They were supposed to help us with generally helping the ML team, preparing evaluation data sets, etc. But we had to repurpose them to splitting. They've been splitting ever since to this day. We wanted to open to a limited user base without any promised turnaround times. If it was an hour, great. If it was 5 days, still okay. And the product was for free this time. A month or two later, human splitting doing great. We collected over 200,000 pages of medical records. We collected them and summarized. That's also great. The big enterprise client really liked the solution. They didn't know that there are humans in loop. We sold as a pure AI solution. I'm still not sure what they were thinking with the 5-day turnaround times, but they loved it. The problem was that there's no progress on auto-splitting altogether, like none. We weren't moving. So a little bit more stress, pressure, back to the drawing board. So again, first principles, what are our problems? The biggest problem was that we couldn't scale with humans in loop, we couldn't launch publicly, we couldn't fully onboard this enterprise client. And the new problem, we're running out of money. And fundraising was ahead of us, so having a new, huge product with a successful launch would be great. So the immediate goal was we needed to scale the product ASAP, no matter what. And the ultimate goal, but we were fine with eventually this happening, was it needed to be fully automatic because humans in loop just don't scale infinitely. This led us to sort of getting creative again, and we started working on two solutions in parallel. The first one, we decided to build a whole new scalable gig marketplace for humans in loop splitting. If you remember correctly, we've already built two marketplaces before, one for transcription and one for notaries in the court reporting business. So we were sort of experienced in this space already. And the second solution that we started working on in parallel was continue with automating the splitting. And we sort of sensed that the AI was there almost. We just weren't sure how much time it would take to get there fully. So several weeks later, it was, I don't remember the exact days, but it was soon before Christmas. The gig marketplace with humans in loop was ready. There was everything from onboarding, training, payments, queuing system, quality assurance, all the building blocks behind every marketplace. And auto-splitting not working still. So more pressure, more stress. Again, this was really before Christmas, and internally we talked about it, like we really have to ship it in January. So we had some, interesting times just ahead of Christmas. So we were really hoping for a Christmas miracle to happen, and it absolutely happened. Gemini 2.0 Flash got launched, and it just started working with this model, which is sort of crazy because we tried all the models, all the different combinations of them, algorithms, architectures, we just couldn't get anything of it. And once we swapped them for Gemini 2.0 Flash, it started to work. So we lived happily ever after. No, we launched publicly with some caveats. The turnaround time was still not immediate like you're used to with AI products, but it was next day because Gemini 2.0 Flash was just in this experimental version with limited rate limits. The infrastructure was failing often because, like I said, often users upload thousands of pages of medical records. I think the largest upload we had was around 16,000 pages, and I mean basically everything breaks in those cases. And the big enterprise client was still on the human-in-loop setup because there was, although the Gemini 2.0 Flash worked nice, there was still a quality drop. So we were hesitant to swap the solutions. But still in this setup, we managed to get to $1 million in estimated annual revenue just a month after launching this product. So great results already. But we still wanted to get rid of this human-in-loop setup for this enterprise client, and we thought these were our options. We could just tell the client or ask them, would you be okay just getting a lower quality product? We didn't even ask. We probably knew the answer to this. We could not tell them at all, but we didn't think it was the right thing to do. We could continue improving the quality, and basically that's what we chose. So how we did it? I maybe like this part of the project the most, or it's definitely one of my most favorite parts of it. We introduced confidence levels, again, something that you could probably introduce in all the other AI products, and we introduced them in a very specific framework, basically defined by two metrics. There was this ratio of high confidence pages to low confidence pages, and then there was this accuracy of high confidence prediction, which basically meant if we tag something as high confident, how likely is it really a correct AI prediction? So the task at hand, and basically customers really, without even telling them about such opportunities, they didn't know anything about AI or confidence levels, but they kept telling us we're fine with AI making errors. They understand AI will probably always make errors, but if we could show them where the mistakes are so they could fix them. So we set ourselves to this goal. We basically wanted to get the ratio high enough, 85, 90%, while keeping the accuracy really, really high at 98, 99%. Then we would show the low confidence levels to users, and we would give them the ability to edit the mistakes, and that would be literally the ultimate experience we could imagine. And that's where we're at right now with the product. This is what we're working on. Right now, I think we're at around 60% of high confidence pages at 98% accuracy. So we still have humans in loop splitting. They're splitting those remaining 40%. And we still, even in those 40% of pages, we show them the AI predictions, and they sort of use them as suggestions. So there is a drop down, and they just select one of the candidates from the drop down list. So that's the whole story from Vratisla's recommendation to build the proof of concept fast, and here we are a year and a half later. After me, Jonáš will talk about this very same product, but with technical insights. So if you have any technical questions, keep them for him. If you have any product questions, here am I. But thank you for your attention.
Thanks, Tomáš. So, are there any questions? Anyone in the audience?
Maybe can you explain what's the hard thing about document splitting? What's like the hard? Oh, sorry. Do you have like multiple documents scanned on one page, or just one page of handwritten text describing events that took place over multiple days? What's the super hard thing about it?
Is that all the data are so different. It's actually difficult for humans. We spend so many hours talking to our annotators, figuring out what are the guidelines for splitting. Sometimes there are multiple dates. Sometimes the dates are called differently. There is like signature date, there is date of service, bunch of other types of dates. Sometimes the whole document is just from one doctor's visit. Other times there are multiple visits on one page. Sometimes there are multiple documents assigned to the same visit. So it's really tons and tons of combinations of everything that could happen. So that's the hard part. It's just really crazy. What are all the different types of medical records and the dates in them?
Yeah, thanks.
Hi. So I wanted to understand how you calculate the 60% confidence or the 98% accuracy, because what's the formula behind it? Is it that you potentially have a benchmark that you set grounding rules for the model where it basically detects or it generates the result and it compares against that benchmark that you deem is of the highest quality and then it assigns a score? Or do you have that system built into the product to determine what that confidence and accuracy is for the generated result?
So we, from all the data we collected from customers, we created a data set. The data set was manually annotated, so we knew which page should have which date and doctor, etc. So we had a data set, and then. Are you asking how we literally computed, how we got the confidence levels technically?
No, if that's how you calculated it, that's fine. But then how do you get the AI to or the model to return or display on your product that this is what the calculated confidence score is?
I think Jonáš will talk about it a little bit more, but basically it's a bunch of handcrafted rules. It's not like we are getting the number from the model, but there's lots of rules that we noticed by looking into the data. For example, handwritten records was one of the rules. If we detect something is handwritten, we automatically tagged it as low confidence because we knew that we're just not capable of doing it correctly for handwritten records. And we had many other similar rules. It was basically just our observation of the model's behavior in specific situations.
Got it. Thank you very much.
Thanks. Any more questions? Anyone?
Awesome story. Thanks. It's great to see what you guys built from it. It's amazing. I'm just wondering, what's the legal implications of you guys being wrong and who bears them? Do you guys bear it, or does the client bear it? And do the clients know that the AI might be wrong even with the high accuracy stuff?
Yeah, good question. It's on the client. We have all kinds of disclaimers throughout the product, like this is AI, it can make mistakes. I think that's sort of became a standard in the industry among other AI products as well, but it's still something that we need to work on going forward. Like, clients are still asking and sending us back the summaries like, hey, what's up, there's a mistake, and we're like, we told you it's AI, there will be mistakes. So I think the users and customers still, at least some of them, need to work on themselves and their understanding of how to work with AI.
Yeah, I think it's really cool how you guys repurpose this thing into like lawyer space and not like medical, actually doctors treating space, because I think like the whole surface of what it makes, what it means to make an error, like the damage is of course much lower in terms of, for example, human lives or something. So I think it's a great pivot.
Well, people tend to forget that people also make mistakes, right? Any more questions? Anyone?
It was actually a good comment, because when we compare the AI outputs to outputs of our annotators, I mean, exactly like you said, humans make mistakes as well. And also attorneys told us, which encouraged us also, that I mean, medical record summaries are usually done by more junior staff, and they often told us that if they have some associate attorney or someone more junior, that they make mistakes as well. So some attorneys were really encouraging in around all the AI makes mistakes problems.
Thanks for the presentation. What was the customer feedback mechanism that you guys decided to go with? Was it a component on the platform, or kind of some sort of survey via email? Or
Oh, you're asking how we decided to build this product?
Yeah, how did you go about the customer feedback mechanism, like through the journey?
I mean, basically, we did a more broader research. We wanted to do something outside of court reporting, our core business. So we talked to many attorneys, we're mapping out their day-to-day lives, and we are trying to identify what are the biggest buckets of work where they spend the most amount of time, and that are potentially possible to be automated with the latest AI. And medical records, among big chunk of our customers, was the absolute winner.
The continuous, like with the feedback from customers? Because I mean, you mentioned that sometimes they'll come back to you and say, hey, there's a mistake here, maybe the AI hallucinated, or was there something where customers could optionally, let's say, click a button, fill out a form, or something like that?
Yeah. We had multiple, or tried to have multiple channels. We had some dedicated design partners, which were sort of customers on call, literally almost friends, which I could just email them or have a phone call with them very quickly. So we had a bunch of these, and then just people are reaching out on their own, like, hey, I found a mistake. Some attorneys were more proactive in this than others, but it was more, natural,
awesome,
naturally
thanks.
evolved.
Last questions, perhaps? Anyone? Doesn't seem like it. In that case, Tomáš, thank you very much. And before we move on to Jonáš and the promised third talk, I would like to give you 10 minutes to maybe run out and have some fresh air, and let's see you in 10 minutes. 2 minutes. So, if you are all ready, then take your place, take something to drink, and let's welcome our next speaker. Our next speaker is Jonáš. He's also from the same company as Tom, and his official title is a VP of Machine Learning and AI Initiatives. So I, of course, asked him what he does, and he's basically responsible for the entire machine learning department. So we have someone really techie here, and I hope for many tech questions after the talk. So without any further ado, Jonáš, there you go.
Hi, hello, good afternoon, and thanks for the introduction. Yes, so my name is Jonáš, and yeah, basically with Tom, with his great talk, we basically started building this medical record. So yeah, basically from day one we lived through this adventure that Tom described, and now I would like to talk a little bit more from the technical perspective, maybe what's behind the scenes of this product that Tom described and showed you. So I will just jump into it. I have quite short outline. Maybe I will just connect to Tom by explaining why medical records are a quite challenging problem from machine learning perspective, and then I will talk about these sub-problems, as we call them. These are like the steps that we run on backend to get from the input to the output in the UI. I will also touch a bit of evaluations and just briefly mention some future of this product as we see it. But maybe to recap, why are medical records so difficult? So you can think about the input space, and it's very diverse from both perspective of the style where you have images and tables and handwritten stuff and these checkboxes and some narrative sections. But also it's very diverse from a content perspective. That means there are sections about X-ray imaging, then there are like sections about laboratory results and treatments and medication lists, etc., etc. So it's very like diverse input space, and that's what makes it quite a challenging problem. So at the top of this slide are these sub-problems, how we call them, and they kind of follow this sequential flow from the input to the output. So the first thing is this like already now famous splitting problem that Tom talked about a lot. So basically we get a PDF and we need to somehow chop it into these like discrete documents. For those we then do this, we call it a Trinity extraction. It's basically for each of these we want to extract the date, facility and the doctors. Then we do the summarization, add these references, and then we do some filters. We put some filters on top of the summarization, and then we have this overview section. It's basically some meta summary of the whole medical record. We do have like section for patient information, so there will be all like the demographic information, maybe some medication history of this patient, because we want to like deduplicate this information from the summaries, because these are the information that tend to be repetitive in many of those documents. So we don't want to be repeated, them to be repeated in summaries, but we kind of deduplicate them and have like this individual patient information section. So diving straight into this splitting problem, this is how you can kind of just visually think about really what we are trying to achieve here. So you have the pages, that's the PDF, and the goal is to basically find the boundaries between the individual documents so that we can then further process them. And that way how we ended up defining what boundary should be is basically whenever a key date or facility changes, there should be a new document boundary. So that sounds relatively straightforward, right? But turns out it's quite challenging problem. There are many ways that make it challenging. First is just the general kind of ambiguity of the task that, as also Tom said, in some of the cases, even as humans, we're having like a very heated fights if there should be a boundary or shouldn't be, and sometimes it's really kind of ambiguous task. So that's one thing, but also there are things like we call them mid-page splits. So it's not like every a new document starts on a new page, but actually there can be new documents starting on a one page and then second one continuing from that page on. Also there are things we call it like a nested document. So you could have, for example, emergency room visit. You have 5 doctors kind of interacting with the patient. Each of them writes a short report, but it's part of this one larger report from the emergency room visit. So we also need to somehow deal with this from like a UX perspective. So this is the setup. This is the solution. Unfortunately, again, the colors are not showing correctly, but that doesn't matter. I will try to just walk you through this solution. We called it like a cascading of basically large language models. This is the solution that Tom described. That was this Christmas miracle, or I don't know how you describe it, but this is kind of what really was kind of the first very highly functioning solution for this splitting problem. This is an illustration using 2 LLMs. In production, we would use 4 of these, but for illustration, it doesn't matter. So what's being displayed here is that we have, we call this like experts, like some LLM that has the goal of splitting. The goal, as I described, is kind of the change in key date and facility. So it's quite simple end goal, but the instruction set, how to kind of get to this end goal, is very different for each of these experts. And what we would do, we would use all like these pages. These experts would each predict their kind of own boundaries, how they deem the best splits the document, and then we would match the predictions, and where the expert matches these regions, they're like high likelihood of being correct kind of splits. And where they disagree, we kind of propagate to the next iteration. And we repeat this cycle until we hit some predefined depth of the cascade. This is a parameter that we can plug into the system, and what kind of propagates all the way to the down of the cascade. These tend to be very kind of ambiguous regions in the PDF, and we would do some final resolution, or actually we do some kind of majority voting there, but we could already mark them as a low confidence. And this is again, the kind of the confidence levels are very like key concept to the whole product. It's something, Tom also talked about a lot, and we kind of try to introduce these confidence levels everywhere we can, basically, throughout the product, because, we know that we cannot solve the problem 100%, but if we can say that we can solve it 90% accurately, and these 10%, like the user should maybe edit through some UX, or our humans fix it for them, that's great. So this would be like how we ended up kind of, I don't want to say solving, it's still unsolved challenge, but we made a lot of progress, and the current quality is pretty good. You saw some metrics. Then there is this like trade-off. You have this like ratio of pages that we mark as high confidence, but the more pages you mark as high confidence, the kind of lower the accuracy of these kind of truly being high confidence. So there is like this trade-off. So we lean towards having as high accuracy as possible, while having the high confidence ratio kind of as high as possible as well. So this is just some kind of implementation slide, just how it works on a backend. Not sure how deep to go here, probably not that much, but just so you know, we use this tool, it's called Temporal IO. It's been very helpful for us for this task, and basically all these steps can be written as like single activities that then run kind of through Temporal in Kubernetes, and it gave us a lot of visibility for like debugging of the system. Also, it's very efficient from like a debugging perspective, because there are like maybe, I don't know, 100 of activities in the whole workflow, maybe even more. But if something breaks, let's say halfway, all the previous activities are cached, and we can just rerun from that step onward. So that was very like critical during the core development, when like everything was breaking, that we could just use this mechanism. So moving on to the second step in the pipeline, that's like this Trinity extraction. Again, unfortunately, the colors are not that visible, but I just wanted to demonstrate in this picture kind of, again, the complexity of the task. So you can see just on the single page, there are multiple different dates. Also, there are multiple different doctors. There is some hospital at the top, but should it be like a Marshfield clinic? Should it be the whole thing? So all these are kind of very almost product decision, how we want to approach it, which date is the most important that would represent this document. And so we would think about this product part from perspective of like retrieval and re-ranking, if you're ever in like, I know, search and stuff, that we, for example, with the dates, we try to optimize first for retrieving as many dates as possible as we find in this document. and then we assign them some categories. So let's say, okay, this is the date of service, this is the date when the document was printed, etc. And then we have some fixed rules against which we sort the dates by their priority. So let's say the date of service has like the highest priority from our list. So that would be like the ranking step. We would select the date of service as the most representative one. What we found working a lot, we use both like the multi-model approach, plus we use the OCRs. So what we found was that if we do OCR, if you know what OCR is, basically just extracting text from image. But one good thing about it, that it's pretty accurate. Like it does get good performance, but it completely breaks the layout of the page. On the other side, some of the multimodal LLMs, they really well understand the layout of the page, but they don't tend to be very good at like extracting a particular information correctly. So we kind of try to combine these two together to kind of get the best of both worlds, and really in all places we introduce this technique, kind of the performance just boosted out of the box. So that was kind of one of the ideas that we used here. We use this like retrieval re-ranking stuff. We then use some kind of this grounding column. There we can do a lot of like creative stuff, but basically we could do like a grounding of the outputs in, let's say, for example, we could even do like a Google search. That's what we do. Like we extract some facility and we can use some tool of the LLM to verify that indeed this is kind of the facility, or like find the most officially sounding name of this facility. Because as you saw, like one facility can be written in many, many ways, and we have to somehow like normalize these across all the documents and select some most officially sounding name. So we would like hit some tool with Google search to just maybe even search the website of that facility and get back the most official name. So with this, we already have the document split. We have this like trinity, the date, facility, and doctors for them. And finally, we can do the summarization. So like traditionally, we approach this task from perspective as like just one very generic medical summarization task. And this goes back to the beginning. As I described, these documents are very, very diverse, both like style perspective as well as content perspective. So what we are now kind of, the way we are now starting to approach it is to basically break it down into much more like fine-grained sub-problems and basically solve each of these sub-problems individually. So we would call these clusters. So here would be some examples of clusters that we identify are very common in the medical records, be like these X-rays or treatments or medical history, for example, etc. So how we would do that is that you have the page, and we would run some feature extraction to extract this like both style and content perspective, content attributes. And basically then we would assign these pages based on these features extracted to their clusters. These clusters we would find in like an unsupervised way kind of during the training. Basically we have many thousands of medical record data as of now, and we could run this feature extraction on each of them and basically find this cluster, run the clustering algorithm and identify these clusters. And once we have these clusters, we can do a lot of like cool stuff with them. We have this like cluster attributes. So basically, for example, every such cluster could have this own instruction set. So it makes intuitively sense that you want to summarize, I know, X-ray images quite differently than you want to summarize laboratory results or medication list, etc. So each of these should have some optimized instruction for them, and you can then build like some LLM evaluations around these clusters. You can even have like a dedicated UIs then into the product again, maybe X-rays, the most optimal UI is just to embed the X-ray image there, whereas for laboratory results, some kind of a table is more fitting, and for some progress notes, like the narrative style might be best. So this is what you get. Also, you get kind of the quality estimation of each cluster, and again, this is where the confidences come into play, that you know, okay, so on X-rays, we do very poorly based on our evaluations, so when in production X-ray images come, we can indicate to user, hey, we're not sure in this on these pages, better check yourself. So again, the confidence levels. And kind of a last of these sub-problems I want to describe here are, again, Tom mentioned this in his talk, but it's the references. So basically we have these bounding box level references, and every basically sentence in a summary has this hyperlink directly to the source. So this was another pillar that kind of we tried to bring into all our AI features, is this verifiability, right? Because you don't want to just show user the summary, but you want them to be able to verify, and ideally on as granular level as possible. So how this works, it's relatively simple. We would have, basically we would split the summary into chunks. The chunk in this context is like a sentence. So let's say there is a sentence from summary. And then we have OCRs. And for our OCR, we not only get like the texts, so that's good, but we have these bounding boxes of these texts. And this is what kind of then allows us to go from the summary all the way to the bounding box level. So now the task is we need to somehow map these text extracts to the summary sentences. And basically how we do that, it's kind of two-step process, because there are many of these OCR segments. So we first like do this like a potential candidates by we run some similarity method. We use TD-IDF, but you could do like embeddings or whatever. And we, for each sentence, have some, let's say, 10 candidates of these OCRs. And then we use LLM that picks the most relevant of these like candidates that kind of cover. Then we promote like a coverage. So every important fact in the sentence should have its reference. And we also promote uniqueness, because you don't want to have like a kind of duplicated references. Because, for example, I know when there is information about blood pressure, and it's mentioned 5 times in the document, we don't want to link to all 5 things, because then in UI you would have like a long list of references. So that's where like how we what the uniqueness part of this is. So it's just one slide how we think about the evaluation. So yeah, there are multiple ways how we approach it. So it's this 2 metrics. Tom talked about them quite extensively. It's this ratio and accuracy. That's how we can evaluate the splitting and trinities, because we can get a evaluation data set for these. So it's kind of easy then to compute these metrics, because we know, okay, is here a boundary or not? So it's like 1 or 0, or what is the date for this document? So it's also you can then compare and compute these. We of course have the client feedback that was like tremendously useful to us, but also we have these like in-house data annotations, annotators, and some LLM-based metrics for these more like generative tasks like summary, which are not like easily evaluatable by some like rigorous metric. And this is just like kind of where we're heading with the product. So I think now from the perspective of the product, the most impactful thing is that basically since we were acquired by Filevine, we can go from like 1 salesperson when we were Parrot to like 200 salespeople to sell this product. So that's great. So we're now integrating it to their platform. And eventually we would like to kind of generalize it so that it's not only for medical data, but many of these concepts can be very like generic for all sorts of documents that the attorney might want to work with as part of their case. So you can then basically throw like anything on it. We can kind of split it and organize it on some kind of timeline, because that's like the common denominator of all these case documents is the timeline, right? There is some accident and everything resolves around that date. And you want to find some patterns and contradictions and evidences around that. And that's basically our kind of vision for where to take this product. So yeah, thank you for your attention.
Thanks, Jonáš. Amazing in-depth talk. Really liked it. Are there any questions in the room? Anyone? Great.
Thank you. It's brilliant speech. Thanks. I have one question. If you identify some pictures in the documents, how do you identify what type of the picture it is? Because there could be X-rays on computed tomography.
Yeah, so usually it's quite clear from the context of that picture. Yeah, but currently the pictures, in my opinion, are not handled are handled suboptimally. That I think ideally we would really like to embed them directly into summary and not try to like describe them by some AI model, because yeah, that's quite dangerous area. But yeah, usually from the context we are able to figure out.
Thanks. Any more questions? Anyone? Perfect.
Thanks. Cool talk. I wonder, those pictures from the slide number 3, they were looking too pretty, like real ones. So are those real medical records? I mean...
I think these are from one of the demo files of our clients, so... Yeah. No, we generated them. No, it's, yeah, from some...
those are a real person. Yeah, so just in case, yeah, you might want to.
Yeah, like but the personal information are like redacted there, so.
No. There wasn't like just in case, like maybe you could use some generated thing next time.
Any more questions? Lovely.
I'm just super interested about your OCR stack, because that's usually a problem. Like some companies are kind of deferring this to large language models. You know, they're using extraction through LLM, but I guess because of the bounding boxes, you guys are using more classical solutions. Maybe can you elaborate on what's the OCR in your OCR?
Yeah, of course. So yeah, I did have like a little bit small section around that. Yeah, basically we use combination of like LLM with multimodal understanding as well as the OCR. And for OCR we use Google's document AI. Like work great from like price perspective, as well as it has many like built-in out-of-the-box features. Not only like OCRs and bounding boxes, but it has, for example, information about the page rotation. And so it happens quite often that some of the pages are rotated because they are maybe scanned. So based on this rotation, we can then correctly rotate them, and then, because the rotated images, they tend to confuse the LLMs a lot. So so yeah, that's the Google Document AI. But we tend to combine it with some of the like large language models.
Yeah, thanks so much.
Any other questions? Anyone? Okay, doesn't seem like it. So in that case, thank you very much for your presentation, Jonáš. and we'll switch the technology to the next speaker. And the next speaker is Matyáš from Developer Experience Heroes, or DX Heroes, which is a company which does developer experience. And, oh, that was fast. So he will talk about how to use AI on large code bases. So I'm really interested in that. Thank you.
Mic check. Hey everyone. Who of you experienced started to hallucinate or break stuff in your repository or suggesting non-existent things? Okay. So I have some strategies that you can use in modern IDEs. Clicker doesn't work. Nope. I'm Matyáš from DX Heroes, and we specialize, or where we help companies with their software delivery, developer experience, creating and maintaining SDKs, maintaining technical documentation, and also implementing AI specifically to their workflows. Because today's AI developer landscape is quite huge. You have multiple options. Things like AI plugins, GitHub Copilot for Visual Studio Code, CLI tools like Claude Code or Aider, AI-first IDEs like Cursor, and what I called English-first IDEs like Lovable, where you can build full-stack applications with few prompts and eventually export the code for further development. And we at DX Heroes, we used mostly Cursor currently for most of our software development. And we use it to build our application, smartstuff.io. Smartstuff is an application where you can build agentic teams that work in parallel on various tasks. You can think of it like running ChatGPTs in deep research mode and working on one thing, each having its own role, just like a real team. And let me share a backstory of our application. The idea started when OpenAI released their real-time API. It was, I think, October 2024. And together with their Whisper models, suddenly it was very easy to build AI real-time chat experiences in your applications. So we tried that. And we also thought, what if we have two devices talking to each other and AI talking to each other? And we tried it. We also tried to set up roles for each AI, like one a product manager, which is angry, and the other software developer, which is delayed on his tasks. But we also thought, like, what is the real problem we can solve with this approach? The approach of having multiple AIs, each with their own role, working together. And we come up with a thing that we do quite often, and that is software analysis. It's a process that involves multiple people, and if you want like a project for your client to end up well, not to exceed a budget by too much, then you need to be very precise about that. So we tried to have this process automated with this approach of AIs working together. We vibe coded or created just with AI and with a few hackathons our MVP. And it was a bunch of Python scripts with a simple user interface where we described all the things for the software analysis. It was running locally. We created some basic orchestrator of the tasks for each AI. And it was great because it was giving us better results than the ChatGPT's deep research mode. And we also come up with even more use cases for this approach, like analyzing data and making reports, or doing market research, or planning your content, automating some administrative tasks, or even monitoring your competition or trends like AI. So we validated this idea with few users, and we created Smartstuff. The domain name, by the way, was found by our AI team, which we created for that. That's pretty cool. But as with every other application that you want to get into production, it started to become more complicated. Well, the tech stack grew, we have multiple languages, and all the infrastructure related to make those AI agents work in the cloud, and a whole bunch of connectors, because smart stuff can connect to basic web search, it can connect to LinkedIn or keyword research tools to handle all the various tasks you want from it. So as our code base grew, we started to see the hallucinations. It started to suggesting non-existent things, especially with the, infrastructure configuration. And the overall core quality went down. So we saw a big slowdown in our development, and as we have a large backlog for our smart stuff, that was quite frustrating. So we're starting to get a bit more strategic about how we work with AI and how we develop new features. We're starting with something quite obvious, and that is improving our prompts. We started to be way more specific and provide examples. So if we were to add a user authentication system, we clearly described which flow the user will go through, which libraries we want to use, or the whole process. We also started to handling context better, because if you just put everything in one chat, you will soon run out of context window, even with today's models. And we also started to using models differently, because you have some faster models that are great for some snippets or quick refactoring. But if you want to implement something more complicated, you can use models like the reasoning models like Claude Sonnet 3.7. But writing the prompts from scratch, it's quite time-consuming and annoying. So we started to creating a lot of rule files around our code base. Rule files are just text files, markdown files, which you can specify, like what your repository is about, where is the overall business logic, and also reference the documentation of your frameworks or templates. So AI suddenly, when you prompt it, has all this context and think much better. We also created a code templates, for example, for adding a new API resource in our backend. So suddenly, the AI doesn't suddenly create everything or generate everything from scratch. It starts to fill in the spots in the templates. So it's way more precise. Idiot Prosper. So yeah, the rule example, just a plain file, which you can specify like in which location you create this new API resource. Here is the template, and make sure that several options. The rule is much longer, it doesn't fit on the screen, but we have multiple of rules like this. But even with multiple rules, in cases where we wanted to implement bigger features and to automate our process even more, the AI was unpredictable. It started to make like large and messy changes, which were hard to validate. So if you ask AI implement this feature at all the context, and you have like 15 changes around your code base and go through them one by one, it's not very good. So we defined a strict system rule for the AI, and we specified the whole workflow it needs to follow for every feature we want to add. We want AI to break down the complex features into smaller tasks. We want AI to create a draft first and even ask us for follow-up questions. We want AI to behave like a software architect first before making sudden changes. And we want to validate a plan with the AI, and the AI will ask us, I want to do it like this, are you okay with that? And then implement it step by step. And then ask AI to review each step. We will review each step, test it, and eventually update our rules or documentation from what we found out. We also implemented some testing practices. As I said, you could use reasoning models that kind of test themselves, they self-prompt themselves in a way. We let AI generate unit tests for critical parts of our code base. And we also added PR reviews from the AI, which are good because they tell you to focus on these critical parts that were changed and have a look to them. And also the pull requests are now like a small documentation. So what we did so far, we improved our prompting, we specified multiple rules in our code base, we set a strict workflow for the AI, and we implemented some testing approaches. So are we wipe coding again now? Well, almost. With all this, it really improved our developer workflow, but AI with the latest models in the most modern IDEs, it still struggles with translation files, Terraform configuration, or AWS or other cloud specifics. But our time to delivery is still much faster with that. But the talk was about large companies or big repositories, right? So the first thing is the people approach. Because if you have companies with tens or hundreds of repositories scattered all over the place, it's good to have someone or even several people that are responsible for handling these repositories and the setups I mentioned previously around all the code bases. We could also have master repositories, because if you are a company of a size of a bank, then you can put in one repository or some part of the domain knowledge, the entity diagram of your database, and as much general information as possible. And then the developers of some individual services can use it as a context if they pull it to their repository, for example, by using Git submodules. And you can distribute the context of your company from documents, file storages, or Atlassian tools through MCP servers, for example. So if you create an MCP server for Confluence, suddenly the developer has access to the pages. He can pull up more reference from some analyst or product owner, and he can even create or update new pages, but be cautious with that. And it's also about AI-friendly delivery in your company. We are currently, as DX Heroes, with some clients implementing behavior-driven development flow in framework Cucumber.js. And this process enables to bring multiple roles into the repository level. So now we have product owners or business analysts working in the repository, creating user stories in Markdown files with all the attachments. We have them create features, which are like the scenarios for the feature, like each individual step, like user needs to be logged in, and when user clicks on this happens. And then, with all this context, the developer can use it to create testing steps, so you can run this whole process in a CI/CD pipeline, and eventually map it to the production code. So, just a user story in your repository, create it as a features. This is Jerkin syntax language for the Cucumber.js framework, for JavaScript or Python, and there are also other options where you specify like the scenarios I mentioned and the background. You need to be logged in with a certain permission. Then the developer can map it to the actual code, production code, and run it in the pipeline. So suddenly you can easily test automatically the outputs the AI is giving to you. And it's also about having AI-first mindset, because we as DX Heroes promote everyone to experiment with the latest tools. We want people to be excited about the technology and not feel like restricted. We want them to share what they have learned, and we have regular workshops with that. And we then promote the proper use of the AI tools with the things we found out internally and for our clients. And eventually, we can, with all this, change the way how we work with AI and make it work on larger repositories. Because the AI developer landscape will keep changing, and we may see things like fully agentic IDE soon, where we will have multiple AIs working together with you in real time on some complex features, without merge conflicts that are currently a problem. We tried that. And we may see developers become more like prompt engineers or more like software architects, and they will guide the AI and work more with the soft roles, so-called. And we might even see AI teams or companies, thanks to our smart stuff, which you should check out. So, thank you, and I will hope the AI will work better for you.
Thank you very much. Are there any questions in the room? Anyone? It's always at the back.
Thank you for the talk. I wanted to ask, you mentioned real-time API. How is it connected to the product? I didn't quite get it, because you can build it with a normal LLM. You don't need real-time API in mind.
Sure, that was like the thing that sparked the idea of AIs working together, like if you put them close to each other. But yeah, technically we have like an orchestration framework, so-called, that manages all the tasks, because you need to like you have output from one agent and then you need to pass it to the other. So that's the technical part. But that was an idea.
Thanks. And the second one is how do you feel about the recent codex release?
Sorry, what?
About the recent codex release by OpenAI, codex. It's like basically
also, the same way, I think yesterday or a few days ago, like GitHub also released like a new user interface feature where you exactly like just say as a prompt a whole feature, and it starts to developing it, testing, and it will deliver you the whole pull request. So yeah, there are things like that that are getting even more powerful. But for like the really hands-on development in the IDEs, we have these rules and stuff I described.
Thanks. Any more questions?
So you were talking about the workflow that you guys implementing the circle.
Mm-hmm.
So how in practice are you guys doing it in a cursor? Are you like doing that workflow in a cursor, or is it like cursor is part of that workflow? You know, how you orchestrate that circle?
Yeah, basically it's
distinct. Yeah.
It's a system rule prompt. So
okay.
It's a prompt that AI will need to like follow every time.
So this kind of goes within the cursor chat, basically.
Exactly.
Okay.
It's included as a context or a reference.
Okay. Thanks. Cool.
Thank you. Any more questions?
Hello. I was wondering why are you using like Claude? It's kind of like the most expensive model, and usually, like as a company, you can get credits and other things for the other models, but with Claude, it's rare. I heard that anybody gets like credits.
Yeah.
So I was wondering, why Claude specifically?
We are like changing the models, as I mentioned, for certain use cases. So if you just want to make like some parts of the code, like then the Gemini Flash models are good for that and much faster. But Claude Sonnet, especially the 3.7, the reasoning version, can be better for the complex edits. If you really want to I want a user authentication system or a payment system in our application, then these models are more expensive, but better with that. Yeah, so general advice could be like experiment with the models in your IDE.
Any other questions? Anyone?
I want to know more about the issues with Terraform. Like what were those, and how did you go about solving them?
Yeah, because the Terraform configuration like is mapped to your infrastructure, but AI doesn't have like access to the exact like cloud services and the latest like releases or versions of them. So that's why, like, it will generate you a Terraform configuration very confidently, but then when you deploy it, you may see problems with that. So yeah, maybe the next step will be like all these cloud providers will like have some MCP servers or other things that make you like pull the context in your repository. That might be great.
Thank you. Any other questions? Doesn't seem like it. In that case, may I have a question? What is the most complex feature you have seen AI develop without assistance, without a human?
The most complex feature, I think it's like handling the orchestration system for the AIs, because as the smart stuff works, we need to have like everything interconnected and delivered to the user, and the user is notified like this tasks in the AI team was done and switch. So big part of this was done like using AI.
Okay, thanks. So thank you very much for being here with us today. Thanks also to the previous speakers, and thanks you for being such a lovely audience with amazing questions. That's everything from the presentations. However, the night is not over, so I think new pizzas arrived, so have something to snack, have something to drink, enjoy the rest of the evening together, and talk about some AI. Thank you for being here.